This video is about Newton's law of gravity and its application to orbits and tides. In the lecture outline, the first set of vocabulary terms is Newton's three laws of motion for how anything moves. The second set of terms is about Newton's law of gravity, and the third set of terms is about orbits and tides. The history of astronomy lecture about Kepler ended with these two questions. Why do planets move the way they do? What causes them to move in elliptical orbits? These questions were answered by perhaps the greatest scientist who ever lived, Isaac Newton. In a sort of historical passing the baton, Newton was born on the same day that Galileo died. An example of Newton's genius was to step back and take a look at the really big picture questions. Why does anything move the way it does? What causes anything to change its motion? Newton developed some basic rules governing the motion of all objects. He used these laws and Kepler's laws to derive his unifying law of gravity. I will first discuss his three laws of motion and then discuss gravity. So, what do you mean by motion or change in motion? I'm going to begin with some vocabulary to make sure we're on the same page because these terms have different definitions than how people usually use the terms. Speed is the distance traveled divided by the time it takes. So many miles per hour or kilometers per second. In the same time interval, greater speed means greater distance traveled. In 2 hours, you can go 120 miles if you're traveling at 60 miles per hour, but you'll go only 10 miles if you're speed walking at 5 miles per hour. To travel the same distance, a faster speed method will do it in less time. To travel 120 miles in your car at 60 miles per hour will take just 2 hours, but speed walking at 5 miles per hour will take 24 hours. Velocity is in italics because how we'll use the term is different than how most people use the word velocity. Proper use of the term velocity includes both the speed and the direction. So you're moving at 60 miles per hour north or 5 miles per hour down. This distinction from speed will be important for orbits. Finally, the term acceleration is also in italics because acceleration is any change in the velocity in a given time interval. That means the speed and/or the direction can change. It also means that slowing down is considered an acceleration. The picture shows two accelerations. A car on the road going around a curve at 18 meters per second is about 40 miles per hour, is changing its direction. An astronomical example is the Hubble Space Telescope in orbit around the Earth at 7,800 meters or 7.8 kilometers per second. Constant speed, but the direction is constantly changing. The last picture has no change in the velocity. Newton took what Galileo found from his experiments that nothing will change its motion unless acted upon by some sort of force, as his, Newton's, first law of motion. This is the property of inertia of an object that describes its tendency to stay at the same velocity, or at rest, unless a force acts on it. If there's a change in motion, then there must be a force at work. Newton then quantified the amount of motion that will occur. The amount of motion depends on the amount of force applied and the amount of inertia the object has, which is also its mass. The mass is the amount of material. Newton's second law says that the amount of force equals the mass multiplied by the acceleration. In the picture, a small force acting on a pillow will send it flying across the room, but giving that same small force to a car will produce a much smaller acceleration. If you want the car to have the same acceleration as the pillow, then you need to apply a much larger force to the car. The amount of greater force needed depends on the mass of the car compared to the mass of the pillow. A car with 1,000 times more mass needs 1,000 times greater force to have the same acceleration as the pillow. Newton's third law says there's always a reaction to whatever you do. For every action force on an object, there's an equal but opposite force by the object. For example, if Andre the Giant is stuck on the ice with Tom Thumb and he pushes Tom Thumb to the right, Andre will feel an equal force from Tom pushing him to the left. Tom will slide to the right with great speed, and Andre will slide to the left with smaller speed, since Andre's mass is larger than Tom's. Next slide. Newton took his three laws of how anything moves and Kepler's third law of orbital motion to figure out the nature of the force called gravity that acted on the planets and moons to make them move in their elliptical orbits in the way they did. Newton's law of gravity explained Kepler's three laws, and it unified the physics of what happened on Earth with what happened in the heavens. This is the universal law of gravity. The picture shows the mathematical formula of gravity, and below that is the English version. The amount of the force of gravity between two objects, F of g in the picture, equals a number called the gravitational constant that is used in all gravity calculations, multiplied by the mass of object number 1, multiplied by the mass of object number 2, all divided by the square of the distance between the two objects. Gravity is always attractive, and it attracts directly toward each object. Let's look at the characteristics of gravity. Since the mass is in the top of the fraction, if you increase the mass of either object, the gravity increases. Since the separation distance is on the bottom of the fraction, if you increase the distance between the objects, the gravity decreases. Gravity weakens with distance. For spherical objects, planets, moons, stars, etc., the distance is measured between the centers of the objects. That's why when you look at something falling on Earth, the separation distance is between the center of the object and the center of the Earth, not the surface of the Earth. Gravity is always attractive. A lump of antimatter will fall toward the center of the Earth just like a lump of ordinary matter. Two clumps of neutral antimatter will pull together just like two clumps of neutral ordinary matter. Gravity depends on just the mass and the distance, nothing else. It does not depend on the composition or the density. A sun made of peanut butter, with the same mass as the hydrogen-helium sun, will pull on the Earth in the same way as the hydrogen-helium star at the center of our solar system. If you were to compress the hydrogen-helium sun, which is 1.4 million kilometers across, down to a sphere just 6 kilometers across, it would be a black hole. How would that affect the orbit of the Earth? Well, remember what gravity depends on. Just the mass and the center-to-center distance. Have those two things changed? No. We would continue to orbit the black hole sun in the same orbit, and it would take the same 1 year to execute. Black holes are dangerous only when you get really close to them. The sixth characteristic explains why gravity is the most important force in astronomy. Although gravity gets small pretty quickly with the square of the distance, it is never zero. It has an infinite range. The bottom picture addresses a common misconception of astronomy students about the gravity between a planet and its star. The gravity force between the two objects is equal but opposite. Remember Newton's third law of motion. The gravity force formula also shows that the forces are equal in amount. However, the accelerations are very different. Like the pillow and car example I used above for Newton's second law of motion, the smaller mass thing is going to have a much larger acceleration. That's why the planet has a very noticeable orbit around the star. Now the star is going to have an acceleration too, and it will have a small orbit. So small that we'll just see the star wobble. If the wobble is periodic, changing back and forth repeatedly and consistently, it means that there is a planet orbiting it. If you know the mass of the star, you can derive the mass of the planet. That's how the first several tens of exoplanets were discovered.